3-eye atlas. Something is missing after the perihelion. This is impossible. For months, the most powerful telescopes on the planet tracked every movement of this interstellar visitor. The 3-eye atlas, the third object originating from another star to enter our solar system, was observed with a mixture of awe and anticipation. Its brightness increased, its trajectory was confirmed, and its approach to the Sun promised to reveal the secrets of its origin. But when it finally crossed the perihelion, the point closest to our star, something changed. Astronomers expected an explosion of activity, a resplendent tail of gases and dust, visible signs of extreme heat. Instead they found silence. No tail, no flash, no visible trace of what had previously made it so spectacular. It was as if a part of the 3-eye atlas had simply disappeared. Data arrived from observatories around the world. The Hubble, the James Webb, the ALMA, the Very Large Telescope all agreed on the same thing. The most recent images showed an almost naked body, without the typical cometary activity, a phenomenon that contradicts the known laws of ice physics and solar radiation. What was lost? Was it destroyed by the heat, or are we facing a structure far more solid and ancient than we imagined? The truth is that what is missing is not just physical material, but something deeper, a clear scientific answer. And that is where the true mystery begins, because what astronomers saw after the perihelion simply has no explanation. The 3-eye atlas was discovered in 2024 by the Atlas Search System in Hawaii. Since then it became the center of attention for the international astronomical community. It was only the third interstellar visitor ever detected, after Oumuamua in 2017 and Borisov in 2019. But this new object was different, brighter, more unpredictable, and with behavior that defied known models. As it approached the Sun, astronomers prepared one of the largest simultaneous observation campaigns in history. The Hubble and the James Webb were directed toward its trajectory. Ground-based observatories in Chile, Spain, and Japan coordinated schedules to record every second of its approach. Everything indicated that the perihelion occurring between the 29th and 30th of October 2025 would be the key moment. But what happened afterward left everyone speechless. The first post-perihelion images did not show the same object. The 3-eye atlas had changed, something that should have been there was no longer there. This video analyzes step by step the most recent scientific data, the confirmed observations, and the possible physical causes behind this phenomenon that no one has yet managed to explain completely. Before we delve into the mystery of the 3-eye atlas and what vanished after perihelion, there are 3 things you need to do right now to engage the scientific community. First, please like this video to bring this impossible discovery to more observers. Second, subscribe and turn on notifications to receive the latest updates on the real-time tracking. And third, go down to the comments section now and write Cosmos to join the global registry of those following this historic event. Please do this now. From its discovery, the 3-eye atlas became one of the most observed bodies in recent times. It was detected for the first time in the year 2024 through the Atlas Search System, a set of telescopes designed to identify near-Earth objects that could represent a threat. But this time what appeared in the images was not something common. Its trajectory was hyperbolic, which indicated that it was not gravitationally bound to the Sun. In other words, it came from outside the solar system. Within days, orbital calculations confirmed what many suspected. We were facing the third known interstellar object after Oumuamua and 2-eye Borisov in 2019. Its official name was recorded as 3-eye atlas. From that moment, a network of observatories around the world began to follow its path. The first surprise came from its photometric behavior. It showed variable brightness, as if it were rotating irregularly or expelling material at intervals. Measurements from the Hubble and the Pan-STARRS telescope showed slight variations in its intensity, something that could be due to the elongated shape of the object or to differences in the reflectivity of its surface. Over time, the data revealed that the 3-eye atlas was slowly approaching the inner solar system, heading toward a zone where solar heat would test its composition. Astronomers from NASA, the European Space Agency, and the European Southern Observatory prepared a coordinated campaign to monitor its behavior. Each instrument had a specific task. Some had to measure its light spectrum, others record its speed and orientation. It was expected that as it approached the Sun it would begin to release gases and dust, as comets do. That was the logical expectation based on what had happened with Borisov, the previous interstellar visitor, which showed a bright coma and a long tail. But as the 3-eye atlas approached, its activity was much less than expected. Its brightness did not increase as much as it should, and telescopes did not detect significant release of material. During its passage through Jupiter's orbit, the James Webb instruments began to record subtle changes in the infrared spectrum. There were indications of water ice, but in unusually low amounts for a body coming from such cold regions of interstellar space. Some researchers proposed that it might have an outer layer of refractory materials, a kind of natural shield that prevented immediate sublimation of the ice. This layer could have formed over millions of years of exposure to interstellar space, where cosmic ray bombardment alters surface compounds. As the object crossed Mars's orbit, excitement grew. Astronomers knew they were facing a unique opportunity to observe directly how an interstellar body reacts to the sun's heat. No laboratory on Earth can reproduce those conditions. Telescopes began to work continuously, collecting images, spectral data, and measurements of its apparent brightness. The three-eye atlas moved faster each day, and its distance to the sun decreased at an impressive speed. The behavior of the three-eye atlas during that period was enigmatic. Some days it seemed to increase its luminosity for no apparent reason, and on others it remained stable. There was no clear correlation with its distance to the sun. Furthermore, the absence of a visible tail drew attention. Typical comets show a clear release of gas and dust as they heat up, but the three-eye atlas seemed to resist that trend. Instead of breaking down, it maintained a compact and defined shape. That was the first sign that something out of the ordinary was happening. Meanwhile, radio observatories tried to detect emissions coming from the object, not as artificial signals, but as natural waves generated by its interaction with the solar wind. In the case of Borisov, for example, weak emissions of this type had been recorded caused by gas ionization, but with the three-eye atlas the results were inconsistent. Some radio telescopes detected faint signals, others saw nothing. The object seemed to defy the expectations of classical cometary physics. The Hubble team managed to capture high-resolution images that showed an elongated shape, though not as much as that of Oumuamua. Its major axis seemed to measure at least a few tens of meters, and the surface reflected sunlight unevenly. These irregularities could be due to differences in material composition or to complex rotation. Polarization analyses indicated that the object was not covered in fine dust, which reinforced the idea of a solid or hardened surface. In parallel, the Subaru telescope in Hawaii and the Roque de los Muchachos Observatory in the Canary Islands confirmed an important detail. The three-eye atlas showed a faint halo of material, but not a typical coma. This suggested extremely low activity. Astronomers began to wonder if it really was a comet or if it was a fragment of some interstellar rocky body. However, orbital measurements were unequivocal. Its origin was not linked to the sun. It had come from the depths of space. As it approached perihelion, expectations reached their peak. Models indicated that the 29th and 30th of October 2025 would be the most critical days. At that distance from the sun, the surface temperature of the object would easily exceed 500 degrees Kelvin, enough to volatilize many compounds. Scientists expected the three-eye atlas to transform visually, showing intense gaseous activity. Observatories synchronized. The Webb, the Hubble, the Very Large Telescope, and the ALMA pointed their instruments toward the same region of the sky, but something did not fit. As data arrived, the first reports showed an object that remained surprisingly stable. Its brightness neither increased nor decreased dramatically, there were no signs of fragmentation or explosive activity. It was as if it were resisting the sun in a way that no known comet could. And it was at that point that astronomers began to realize they were witnessing something unprecedented. The final pass before perihelion became a race against time. Every observatory wanted to obtain the definitive image. Some astronomers even adjusted their telescopes manually to follow the trajectory in real time. What everyone expected was to see an explosion of gases or a sudden change in brightness. But what they actually captured was something else, a cosmic silence, an absolute calm in the midst of the hottest point of its journey. The three-eye atlas had survived intact, without showing the slightest sign of disintegration. No visible tail, no bright coma, no burst of activity. What should have happened according to physical laws did not happen. Instruments recorded something impossible. The interstellar visitor had crossed perihelion without detectable mass loss. And that would be only the beginning of the mystery. The perihelion days were awaited as a historic event. From weeks before, space and ground-based observatories had prepared every instrument with precision. The James Webb had already adjusted its orientation with several days of anticipation, calculating the exact angles to capture the moment when the three-eye atlas reached its closest point to the sun. On Earth, the Hubble orbited attentively, programmed to take rapid sequences of images. The Very Large Telescope in Chile and the ALMA radio telescopes synchronized to measure gas composition and surface temperature. Everything was ready to witness the instant when solar radiation transformed the interstellar body. On the 29th of October 2025, the first records began to arrive. At that time, the object was a little more than 0.8 astronomical units from the Sun, traveling at a speed close to 70 kilometers per second. The calculated temperature on its surface exceeded 500 degrees Kelvin, and any volatile compound, water, carbon dioxide, methane, should have sublimated almost immediately. In theory, the 3-eye atlas should show intense gas emission, an increase in its brightness, and the development of a visible coma. However, the first images showed an unusually stable object, with no trace of evident activity. The James Webb, observing in the mid-infrared, detected a surprisingly flat emission curve. There were no signs of massive release of vapor or suspended particles. In other words, the object was not behaving like a comet. The Webb recorded a surface with high reflectivity and anomalously uniform temperatures, something incompatible with a structure formed by ice. That same day, the Hubble confirmed the result with a series of high-resolution images. The 3-eye atlas presented no tail or diffuse halo. It was a compact body with uniform brightness. The news spread quickly among observation centers. Teams began to review the data for calibration errors. It could be an instrumental failure, a wrong angle, or an effect of the solar background, but all analyses agreed. The results were consistent. The 3-eye atlas was passing through its perihelion without showing the expected thermal signs. That challenged the most basic thermodynamic predictions. During the following hours, the object moved behind the Sun as seen from Earth, which temporarily interrupted direct observations. However, the instruments of the Solar and Heliospheric Observatory and the Solar Orbiter continued monitoring from different orbital positions. Both recorded a crucial datum. There was no visible material ejection, not even in ultraviolet wavelengths. Solar radiation struck the surface of the 3-eye atlas, but it did not respond like a body composed of ice or dust. It was as if it were formed by a substance that withstood extreme temperatures without altering. When the object emerged from the other side of the Sun, expectation was enormous. Scientists expected that as temperature decreased, changes would be observed, perhaps fragmentation or an alteration in its brightness curve. But telescopes detected none of that. The object remained intact, with luminosity almost identical to that before perihelion. That was the moment when comparisons with previous visitors began. Oumuamua, the first, had shown strange behavior, accelerating without apparent explanation. Borisov, in contrast, behaved like a typical comet, releasing gases and gradually fragmenting. The 3-eye atlas seemed to combine characteristics of both. An interstellar trajectory, but a resistance that defied known physical norms. High-resolution spectral analyses from the Webb and others indicated a total absence of water emission lines and other common volatiles. Instead, the spectrum showed a surface coated with complex carbonaceous compounds and hardened silicates. This type of material can withstand high temperatures without sublimating, which would explain the lack of visible activity. However, the apparent density of the object, calculated from its rotational movement, suggested a structure much lighter than expected, which posed a difficult contradiction to resolve. On the 30th of October, analysis teams from the Paris Observatory and the Institute of Astrophysics of the Canary Islands published preliminary reports. In them it was noted that the 3-eye atlas had shown minimal brightness loss, barely 5% compared to previous days, which was insufficient to explain active sublimation. In simple terms, there were no signs of disintegration. This behavior led several scientists to reconsider traditional classifications of interstellar objects. Perhaps, more than a comet, the 3-eye atlas was a fragment of some planet or a residue from a collision in another stellar system coated with a layer of refractory materials. Meanwhile, ground-based observatories continued observing. The Subaru telescope detected a periodic variation in its brightness, indicating that the object was rotating slowly. That rotation of approximately 8 hours was more stable than expected for a body that had just passed so close to the Sun. Normally thermal stresses would cause irregular rotation or even fragmentation. But none of that happened. The stability of the 3-eye atlas continued to defy any explanation. The phenomenon attracted the attention not only of astronomers, but also of physicists specialized in exotic materials and small body dynamics. Some began to study numerical simulations to determine if a metallic structure could withstand such conditions. Models showed that an object coated with silicates and amorphous carbon with extremely low density could survive solar radiation without releasing visible gases. That would explain the observed resistance, though not the total absence of a tail. The most surprising observation came hours after the exact perihelion passage. The Gemini telescope captured a reflection on the object's surface, a short and very localized flash. That sudden brightness lasted less than 3 seconds and then disappeared. Some suggested it was a specular rotation, a reflection of sunlight on a polished or crystalline area of the three-eye atlas. Others interpreted it as an indication of a surface crack that momentarily reflected light, but no subsequent image repeated the phenomenon. The mystery deepened. For scientists, the passage of the three-eye atlas through perihelion was a demonstration of how little we understand about interstellar objects. Each one seems to break a different rule. What should have been an active comet turned out to be a passive body. What should sublimate remained solid, and what should show a tail presented itself as an immobile point of light. Questions multiplied. What kind of material could resist the sun's heat without altering? It could be a rock formed under extreme conditions outside the solar system or a nucleus that already lost its volatile compounds millions of years ago in another stellar system. As the three-eye atlas moved away from the sun, attention did not diminish. Every new measurement was analyzed in extreme detail. Astronomers sought any sign of change in its brightness or trajectory that could give clues about its internal structure. But the visitor continued its course indifferently, with the same calm with which it had arrived. When official reports were published, a phrase was repeated in many of them. The three-eye atlas has defied our expectations. That was not an exaggeration. For the first time, scientists faced an interstellar body that seemed to resist perihelion without altering, as if it were made of an unknown material or protected by a layer that completely isolated it from solar heat. And although scientific explanations began to form, the truth was that the phenomenon remained an anomaly within the known laws of cometary physics. What no one could deny was the fundamental fact. Something had changed. Telescopes had captured an object that seemed to have lost part of its original brightness, but not due to disintegration, but due to the absence of what previously made it so peculiar. Something was missing in the three-eye atlas, something that until then they could not identify, but whose absence would become more evident with observations in the following weeks. When post-perihelion observations began to arrive, the astronomical community found itself facing a phenomenon that simply did not fit. During the previous weeks, the three-eye atlas had been monitored minute by minute, and everything indicated that its behavior should follow the known pattern of any icy body approaching the sun. But what was observed after the 30th of October was the opposite. The object seemed to have lost something fundamental, something that had characterized it throughout its trajectory. There were no longer indications of the faint gas jets that had been detected in previous months, nor any trace of a possible tail. It was as if the three-eye atlas had changed its nature from one day to the next. The James Webb, which had resumed observation from its position at the Lagrange point L2, recorded the first spectra after perihelion. The data were clear. The object's brightness had decreased slightly, but its apparent composition had changed notably. There were no longer spectral traces of the volatile compounds that had previously been observed, such as frozen water or carbon monoxide. Instead, the surface showed reflectance characteristic of denser and darker materials, probably silicates or oxidized metallic compounds. This abrupt change puzzled researchers because no physical model predicted such a rapid transformation without a process of fragmentation or visible mass loss. Initial reports from the European Southern Observatory were cautious. They indicated that the three-eye atlas had lost all signs of known cometary activity, which implied that at an observational level it now behaved like an inert asteroid. However, its brightness did not match that of a conventional rocky body. There were very subtle periodic variations that suggested an irregular surface, possibly covered by a layer of material altered by the extreme heat of perihelion. Some astronomers began to speak of a surface carbonization phenomenon, in which organic compounds exposed to heat transform into a dark layer that absorbs solar radiation and reduces reflectivity. This could partially explain the brightness loss, but did not justify the complete disappearance of gaseous activity. The ALMA telescope, observing in millimeter wavelengths, sought signs of residual gas or fine dust. What it found was absolute silence, not even a weak emission signal of carbon monoxide or cyanogen, gases that normally persist even in aged comets. The three-eye atlas seemed to have entered a phase of total inactivity, something that no interstellar visitor had shown until then. Oumuamua never had a coma, but showed a non-gravitational acceleration that is still not fully understood. Borisov, in contrast, released so much material that it partially disintegrated. But the 3I Atlas seemed to defy both behaviors, neither anomalous acceleration nor active sublimation. It was a body that simply followed its course indifferently with unsettling stability. Researchers began to review previous records, compared images from weeks before perihelion with new shots, and discovered something more intriguing. Not only had the tail disappeared, but a faint halo that previously surrounded the object was also missing, probably formed by slowly released dust particles. That halo had vanished completely. The absence of this envelope drastically changed the way sunlight interacted with the surface, which explained part of the alteration in its brightness, but not the physical phenomenon behind that loss. Some proposed that during perihelion the extreme heat had sealed surface pores, trapping gases inside the body and preventing new releases. Others suggested that the volatile material had simply been depleted, but even that explanation was incomplete, since at least a slight trace of residual emission would be expected, which was not observed. As weeks progressed, telescopes continued to report the same thing, a stable point of light without signs of chaotic variability. In a way that made the 3I Atlas even more interesting. Its apparent calm hid a history of profound physical transformations. Thermal analyses showed that the surface, although darker, retained low and constant temperatures, indicating surprising efficiency in dissipating heat. This behavior suggested that its internal structure contained voids that acted as natural insulators. It was as if the 3I Atlas were designed to resist the sun's fire, a characteristic that, although completely natural, was extremely unusual for a body formed outside the solar system. The mystery grew when follow-up data from the Hubble revealed that the object's shape had not changed. Most comets, after such a close perihelion, show some visible morphological alteration, whether loss of fragments or changes in their rotation axis. The 3I Atlas, however, remained the same. No cracks, no fragments, no dust clouds floating around. Everything pointed to it having endured the experience without visible damage. That resistance puzzled scientists, who began to pose new hypotheses about the nature of interstellar objects. Perhaps some thought these bodies are not simple icy remnants, but composed of materials that formed under extreme conditions in inner zones of distant stellar systems and then were expelled by gravitational interactions. The Subaru telescope again recorded the object's brightness at the end of November. To everyone's surprise, the 3I Atlas continued to reflect the same amount of light, indicating that it was not fragmenting or losing mass significantly. This reinforced the theory that the volatile material had been completely depleted and that now only a solid, resistant, and stable nucleus remained. In a way, the object had transformed into a cosmic fossil, a silent relic from a distant stellar system, traveling through space without leaving a visible trace of its active past. Despite everything, there was something that continued to worry astronomers: the loss of a spectral component that had been recorded weeks before. Initial observations from the James Webb Space Telescope had shown a weak line associated with cyanogen, a gas common in comets. After perihelion, that line disappeared completely. It was not a simple change in intensity, but a total elimination. Some researchers interpreted it as a sign that the 3I Atlas had undergone an irreversible chemical alteration, perhaps by intense solar radiation that destroyed surface molecules. However, the speed of the process remained a mystery. In less than 48 hours, the object's spectrum had changed radically. Comparison between pre- and post-images showed another detail: a slight change in the object's color. Before perihelion, its tone was slightly greenish, indicative of certain volatile compounds that reflect at specific wavelengths of the visible spectrum. After perihelion, that tone disappeared. The object now reflected a more neutral light, tending toward dark gray. Scientists described this change as a chromatic loss, which reinforced the idea that a chemical alteration had occurred on the surface. The 3I Atlas was no longer the same. Something had evaporated, decomposed, or transformed, leaving behind a denser, opaque, and silent body. Astronomers from the Max Planck Institute published a brief statement. The 3I Atlas has passed from an active state to an inert state. There is no evidence of fragmentation or activity after perihelion. This description, though simple, summarized the magnitude of the discovery. It was the first time an interstellar object showed such a drastically changing behavior, going from having signs of activity to becoming a stable and inert mass in a matter of days. What disappeared was not a visible physical part, but its active essence, its ability to interact with the solar environment. That absence, That something missing was not just a matter of composition, it was a break with what was believed to be understood about bodies coming from interstellar space. The 3I Atlas had survived, yes, but it had also lost its dynamic character, its gaseous breath, its changing light. It had been reduced to a mute fragment, reflecting sunlight without responding to it. And in that quietness, astronomers began to find new questions deeper than the answers they expected. What processes can erase the activity of an interstellar body so quickly? And what does that tell us about its origin, about the systems that formed it? The mystery of what is missing remains unsolved, and as the 3I Atlas slowly moves away from the Sun, the unknown becomes even greater because what disappeared cannot be measured precisely again. What was lost, it seems, was lost forever. In early November 2025, consolidated data from space observatories began to flow to analysis centers in the United States, Europe, and Japan. The first calibrated images from the James Webb and the Hubble confirmed without margin of error that the 3I Atlas no longer showed any sign of gaseous activity. The Webb's infrared instruments recorded a stable temperature surface without thermal peaks, indicating that the object was not expelling vapor or dust. Visually, the Hubble detected a compact body with regular brightness and without any indication of a coma or tail. It was a disconcerting image, an interstellar object that had survived solar heat without showing the expected changes. Astronomers began to compare these observations with previous models. Thermal calculations indicated that the 3I Atlas should have lost at least 15% of its surface mass if it were composed of ice and dust. But reality showed the opposite. Not only was there no visible loss, but the object seemed to preserve its structure intact. Laboratory simulations showed that a body of that size subjected to temperatures of several hundred degrees Kelvin should have fragmented or partially volatilized. However, the 3I Atlas behaved as if it had a protective layer, an envelope that kept it stable against solar radiation. Spectral analysis revealed something even more intriguing. The wavelengths recorded by the Webb showed a signature characteristic of complex carbon materials, similar to those found in carbonaceous chondrite meteorites or in remnants of asteroids that have suffered intense heat alterations. This finding suggested that the 3I Atlas might not be a classic comet, but a mixed object composed of rocky materials coated with organic compounds degraded over time. In that scenario, the lack of a tail would not be so strange because the volatiles that could have formed it would have been depleted millions of years ago during its interstellar journey. Teams from the European Southern Observatory used the Very Large Telescope to obtain high-resolution images. The photographs showed a slightly elongated silhouette with an aspect ratio estimated at 3:1, similar to the shape of a cigar. However, its brightness was more uniform than that of Oumuamua, suggesting slow and stable rotation. This rotational stability indicated that the object had not suffered significant alterations during its perihelion passage. Calculations of its rotational period based on light variation indicated a rotation of approximately 8.2 hours, consistent with data obtained before the solar approach. This was another fact that puzzled scientists. Even after perihelion, the 3I Atlas behaved exactly the same as before, as if the sun had had no effect on it. Follow-up images from the Subaru telescope in Hawaii, taken in the first week of November, showed an additional detail. The object's surface appeared darker than in previous shots. This decrease in albedo matched what was expected from surface carbonization. When exposed to high temperatures, volatile organic materials can decompose, leaving a layer of carbon-rich residues. This process could explain why the 3I Atlas seemed to have lost its characteristic bluish-green brightness before perihelion. In the new images, the object reflected a more neutral, almost grayish light, indicating a real chemical change on its surface. The NASA analysis team, led by astrophysicist Laura Campos, published a technical report describing the phenomenon as complete outgassing without visible fragmentation. In other words, the 3I Atlas had released or transformed its volatile compounds during perihelion, but without producing an observable tail. This was an absolute rarity. No known body had shown such a clean transition, without structural loss or visible matter ejection. Under normal conditions, comets show a brightness increase before perihelion and then an irregular decrease due to sublimation. The 3I Atlas, in contrast, showed a smooth, almost flat light curve, with a constant and symmetric brightness reduction. That symmetry indicated that the physical process that occurred on its surface was uniform, without explosions or chaotic detachments. Spectra obtained by the Keck telescope reinforced the idea that the object was composed of extremely resistant materials. Traces of olivine and pyroxene were identified, minerals common in rocky bodies, along with weak signals of amorphous carbon. This combination recalled Type D and C asteroids from the outer belt, which also present dark surfaces rich in modified organic compounds. If the 3I Atlas shared these characteristics, then it could have been a fragment of a rocky planet or a primitive body expelled from another stellar system millions of years ago. One of the most discussed images was taken by the Hubble on the 5th of November. In it, the 3I Atlas appears as a sharp point of light, without any diffuse extension. Technicians carefully reviewed long exposures looking for traces of dust or scattering, but found nothing. This result was confirmed by the Hubble Space Telescope imaging spectrograph a few days later. The object completely lacked a coma, even in infrared wavelengths. This meant there was no thermal emission from gases or particles floating around it. It was a totally passive body reflecting sunlight without emitting additional energy. The visual silence was so absolute that some researchers began to question whether the 3I Atlas should continue to be considered a comet. The definitions of the International Astronomical Union were not prepared for a case like this. If an interstellar object shows no cometary activity, but also does not have the density of an asteroid, what category does it fall into? The debate ignited in conferences and specialized articles. Some proposed a new classification. Inert interstellar objects, bodies that have lost all their activity, but retain an irregular and composite structure. Others preferred to keep the label 3I simply as a designation of origin, without implications about its physical nature. The most detailed images from the Webb even allowed calculation of the degree of reflection and surface roughness. Three-dimensional models indicated a granulated texture with darker zones interspersed with slightly more reflective areas. This heterogeneity could be due to ancient fractures or uneven exposure to the sun's heat. In any case, the surface seemed solid and stable without indications of active erosion. The finding was so surprising that the journal Nature Astronomy dedicated a special article to the thermal stability of the 3I Atlas, highlighting that its resistance exceeded by several orders of magnitude what was expected for bodies of its size. As days passed, comparison between images revealed another interesting datum. The object had maintained its rotation axis without notable changes. This ruled out that perihelion heat had affected its internal dynamics. If there were cavities or gas pockets, internal pressure would have altered its spin. But none of that happened. The 3I Atlas rotated as if nothing had happened. Scientists from the European Space Agency conducted a reflectivity study using records from the Solar Orbiter probe, which had briefly captured the object from a different angle than Earth. The results confirmed the low reflectance and absence of light scattering, reinforcing the idea that there were no particles floating around. The object was a pure, compact, and surprisingly stable nucleus. For astronomers, these images and data were more than simple observations. They were a window into a type of material that does not exist in our nearby environment. The 3I Atlas represented a fragment from another stellar system, a time capsule that had crossed space for millions of years without disintegrating. The information contained in its spectra could help understand how planets form in other places in the cosmos and why some bodies are so resistant to extreme thermal forces. However, the absence continued to be the most unsettling. The images clearly showed what was there. A solid, stable, dark and silent body, but they also showed what was not. The activity, the movement, the release of gases, the dynamic life that defines comets, that lack of reaction to the sun, that impossible calm, was the most compelling evidence that something had disappeared. What was missing was not visible, but its absence was as evident as light itself. And although scientists began to accept the data, the general feeling was one of bewilderment, because every image confirmed an uncomfortable truth. The 3I Atlas had survived the sun's fire without transforming, without breaking, and without explaining how. It was the quietest paradox in the solar system, a visitor that had defied visible physics. Before perihelion, images of the 3I Atlas showed an active visitor, full of signals that at the time seemed normal for a body approaching the sun. The first time its structure was observed in detail, in mid-2025, astronomers noticed something that caught attention: an elongated, irregular shape, similar to a solid fragment with a surface that reflected light unevenly. Brightness variations indicated that the object rotated slowly, showing clearer and darker zones, as if composed of different materials. That behavior matched that of a young interstellar comet, charged with gases trapped under its surface. During the months of July and August, telescopes around the world continued to record signs of activity in the 3I Atlas. There were sporadic brightness peaks, slight increases in luminosity interpreted as gas or dust emissions. On several occasions, the Subaru telescope and Pan-STARRS detected indications of a weak coma, a faint envelope of material expelled by solar heat. That coma extended only a few thousand kilometers, very small compared to solar system comets, but enough to confirm that the 3I Atlas was alive, interacting with the environment. At that time, astronomers were convinced that its perihelion passage would be spectacular. The weeks before the 29th of October were intense. Observation teams took turns to capture every change in its brightness. The object showed a slight greenish tone, a clear sign of the presence of carbon and cyanogen compounds that usually produce that color when excited by solar radiation. Spectra from the James Webb confirmed those chemical signatures. The lines of cyanogen and dicarbon were visible and consistent. That meant the 3I Atlas contained volatiles probably trapped under a hardened surface layer. It was, in appearance, a typical interstellar comet, but with a composition that mixed ice, silicates, and organic matter. In the days when it crossed Mars's orbit, its brightness increased almost 40%. Scientists thought solar heat was beginning to release frozen gases inside it. The Keck telescope recorded photometric variations suggesting irregular release, perhaps in jets emerging from surface cracks. That behavior was exactly what was expected. That is why, when the object passed perihelion and showed none of that, the surprise was so great what had been seen before simply disappeared. September records even showed a small asymmetry in its luminosity, indication that one of its faces was emitting more material than the other. Some astronomers speculated that the 3I Atlas might have a kind of localized active region, similar to hot spots on solar system comets. But that zone, if it existed, turned off completely after perihelion. Cometary activity models failed to explain why a body that showed active behavior before maximum heating suddenly became inert right after the hottest point of its trajectory. In southern hemisphere observatories, the 3I Atlas became the protagonist of dozens of observation nights. The Very Large Telescope managed to capture sequences in which micro-variations in brightness were observed, a pattern that, according to experts, indicated complex rotation or a slight wobble in its axis. That movement was consistent with unequal gas emission, a kind of irregular breath that made the object rotate slowly. It was an unequivocal sign of internal activity. However, after perihelion, that wobble disappeared. Its rotation became more stable, more uniform, as if the body had reached a new equilibrium. ALMA teams also detected traces of volatile molecules before perihelion. Observations in millimeter wavelengths revealed the presence of carbon monoxide, though in low concentrations. These molecules are sensitive to heat and release easily when the ice containing them sublimates. The detection was weak, but enough to confirm that the 3I Atlas was not a simple piece of rock. It contained material that responded to the sun. The complete disappearance of those signals after perihelion was what most puzzled researchers. Thermal analyses showed that the surface of the 3I Atlas had low conductivity. This means that sun's heat did not penetrate deeply into its interior, which could explain why its activity was so mild. Only a small fraction of the material heated enough to sublimate. But even in that scenario, perihelion should have produced an explosion of activity, something that never happened. Instead, everything that previously showed life and change extinguished without leaving a trace. One of the most interesting comparisons came from the joint study between NASA and the European Space Agency. By superimposing Webb images from September with those from November, it was noted that the object had completely lost the diffuse envelope that previously accompanied it. That envelope, though weak, contained dust and small particles that scattered light. Its disappearance implied that something physical had been lost. The lightest materials, the remnants of its outer layer, had volatilized or compacted in such a way that they could no longer reflect light. The transition was so radical that many began to describe it as an interstellar shutdown. The 3I Atlas not only changed appearance, it also changed character. It went from being a weakly active comet to becoming a silent body, almost indifferent to the sun. Comparisons with Oumuamua and Borisov multiplied, but none matched completely. While Oumuamua had shown an inexplicable anomalous acceleration and Borisov had behaved like a classic comet, the 3I Atlas combined characteristics of both. It had the shape of one and the resistance of the other, but none of their reactions. It was as if something that previously pulsed inside it had extinguished forever. Astronomers reviewed every archive looking for lost signals. They reprocessed images from August and September. They applied algorithms to detect dust traces or subtle changes in brightness. They found that before perihelion, the the 3I Atlas had a slight pulsating emission pattern, a variation that repeated every certain time. That signal disappeared completely after the 30th of October. What was there before, that minimal breath of gases, no longer existed. The most notable was that the general structure of the object remained the same. It did not fragment, did not lose mass, did not show new cracks. What was lost was invisible, its ability to react to heat, its internal activity. For scientists, that implied that the 3I Atlas had depleted its volatile reserve and had become a purely rocky body. In other words, what was previously an interstellar comet was now an interstellar asteroid, a fossil remnant traveling in silence. Researchers from the Institute of Astrophysics of Paris proposed a theory. The 3I Atlas could have had a crust hardened by cosmic radiation during its long journey through interstellar space. That crust would have acted as a shell, trapping gases inside and releasing them slowly as it approached the sun. Once that layer heated to its maximum, it sealed completely, stopping all sublimation. What had previously been a source of activity transformed into an impenetrable barrier. That explanation, though plausible, still failed to resolve the most unsettling question. Why was the change so sudden and absolute? The data showed no gradual transition, but an almost instantaneous leap. Between the last active observations and the first images after perihelion, less than 48 hours had passed. In that span, the 3I Atlas had stopped emitting gases, lost its characteristic brightness, and become a mute body. It was as if something essential had switched off inside it. What had been there before, the variable light, the gas, the greenish color, the barely perceptible small tail, no longer existed, and what remained was a cosmic silence that no instrument could fully explain. The 3I Atlas had survived, yes, but at an invisible cost. It had lost what made it recognizable, its changing nature, its breath of ice and dust. What was missing now could not be measured, it could only be confirmed that it was no longer there. The reaction from the scientific community was swift. In the hours and days following perihelion, the world's major observatories began exchanging data in real time, trying to confirm that the measurements were correct. The James Webb, the Hubble, the ALMA, the Very Large Telescope, and dozens of smaller telescopes all agreed on the same thing. The 3I Atlas had become inactive, silent, without emission signals. At first, some researchers thought it was a misinterpretation or an effect of luminous saturation caused by proximity to the sun. But the records, carefully calibrated, showed that the phenomenon was real. What had previously been considered one of the most anticipated approaches of the decade suddenly became a mystery that defied logic. At NASA headquarters, the Near-Sun Object Analysis team received the first reports with caution. The James Webb data were consistent with those from the Hubble, and both matched measurements from ground-based radio telescopes. There was no gas, no dust, no signs of activity. Laura Campos, one of the lead astrophysicists on the project, described the moment in an interview. It was disconcerting. We expected an explosion of energy, a massive release of material, something to confirm our thermal models. But what we got was the opposite, a completely still body. That should not be possible. In Europe, the European Southern Observatory convened an emergency committee to review the Very Large Telescope images. In an internal transmission, astronomers compared the 3I Atlas observations with those of solar system comets that had passed through perihelion under similar conditions. In all known cases, even the oldest and most dormant ones, some type of residual emission was recorded. The 3I Atlas broke that rule. Its behavior did not fit into any established category. It was an interstellar object that had crossed the hottest point of its trajectory without showing a single sign of change. The debate quickly spread. Some researchers proposed that the 3I Atlas might have depleted all its volatiles long before entering the solar system and that what had been observed before perihelion was not true cometary activity, but light reflections and geometric variations. However, that explanation did not match the spectra recorded weeks earlier, where real gases had been detected, not optical illusions. Others suggested that extreme heat had altered its surface in an unexpected way, sealing pores and preventing internal gases from escaping. But again, the speed of the change and the total absence of floating residues made that idea difficult to sustain. Meanwhile, scientists from the Institute of Astrophysics of the Canary Islands issued a statement calling for caution before drawing hasty conclusions. They noted that interstellar objects could have physical properties very different from those of bodies formed in the solar system due to their origins and eras of exposure to cosmic radiation. We cannot assume they react the same to solar heat, the report said. These objects have survived millions of years of interstellar erosion. It is possible that their surface is much more resistant than we imagine. The topic quickly attracted attention from universities and research centers worldwide. In Japan, the Subaru Observatory reanalyzed all prior data and discovered that the 3I Atlas had unusually low reflectivity, even before perihelion. That implied solar radiation was affecting only the outer layer without penetrating deeply. If the surface layer acted as a thermal insulator, heat would not have reached the internal volatile materials, and thus no visible ejection would have occurred. This model explained part of the mystery, but did not resolve it completely. At Harvard University, a team led by astrophysicist Mariana Perez attempted to recreate the phenomenon in simulations using heat transfer models. They calculated that a body with an amorphous carbon layer a few millimeters thick could withstand temperatures near perihelion without structural damage. But for that material to form, the object would have had to undergo intense cosmic radiation processes for millions of years, something that would only occur on the edges of active interstellar regions. That possibility opened a new line of research. And if the 3I Atlas was a fragment ejected from a very ancient star formation zone, hardened to the extreme by time, scientists at NASA's Goddard Center considered another hypothesis, that the 3I Atlas had not shut down, but its activity had changed form. If the released gas contained no molecules that reflected visible light, it might have gone unnoticed by optical telescopes. However, infrared and radio instruments also detected no emissions, weakening this idea. Across all observation ranges, the object remained inert. Scientific press began to speak of the impossible comet. Headlines multiplied. The interstellar visitor that defied the sun, the object that did not melt, 3I Atlas, and the physics that does not fit. Articles in Science and Nature adopted a more prudent tone, focusing on data and avoiding speculation. But even in those media, the word mystery appeared repeatedly. The 3I Atlas had become a unique case, a phenomenon that forced a review of theories on how interstellar materials react to solar radiation. Teams that had followed the object's trajectory for months felt a mixture of disappointment and awe. Disappointment because they expected a visual spectacle. Awe because what they obtained was even more valuable, a scientific exception. The silence of the 3I Atlas contained deeper information than any gas explosion. It was an opportunity to study a body that had remained practically intact since its formation, a witness to the birth of another solar system. In an international video conference organized by the European Space Agency, several specialists agreed on a key point. The 3I Atlas could represent a completely new category of interstellar objects. Not comets, not asteroids, but hardened hybrid fragments from slow chemical processes and prolonged exposure to cosmic rays. Its stability was not an error but a clue. In the words of German astronomer Heiko Müller, the 3I Atlas did not behave as we expected because it was not born where our comets are born. It is the product of a different environment with thermal and chemical laws that we are just beginning to understand. International collaboration intensified. Laboratories worldwide began reproducing the extreme thermal conditions the 3I Atlas had experienced to observe how different material types reacted. It was discovered that some organic compounds, after millions of years of cosmic radiation exposure, transform into highly resistant amorphous structures, capable of withstanding temperatures higher than expected without sublimating. This type of material could be present in the 3I Atlas, explaining its unusual resistance. Scientists also realized that the 3I Atlas offered a unique opportunity to study the long-term evolution of interstellar objects. If it had truly gone from active to inert in a matter of hours, that implied the object's surface had reached a critical point of physical transformation. The idea that a body could seal itself after extreme solar exposure began to gain ground. There was talk of a cosmic vitrification process in which the surface melts and solidifies rapidly, forming an impermeable layer that prevents future sublimations. The scientific community, however, maintained prudence. No one wanted to fall into simplistic explanations or sensationalist comparisons. The 3I Atlas remained a natural phenomenon, no matter how strange it seemed. There was nothing outside physics or measurable, just a combination of variables not yet fully understood. The mystery was not a denial of science, but an invitation to expand it. The final consensus among researchers was clear. What happened with the 3I Atlas was not an observation error or an isolated anomaly. It was a reminder that interstellar objects are witnesses to conditions that do not exist in our environment and that some of them can withstand the sun's fire unmoved. In laboratories, models began to update. Parameters were added to consider hardened materials, carbonized layers, and pores sealed by cosmic radiation. The mystery gradually transformed into knowledge, but despite theories, equations and simulations, one question remained unanswered. What exactly did the 3I Atlas lose during its perihelion passage? There were no fragments, no gases, no dust. The only thing missing was something intangible, its former active nature, its cosmic breath. What disappeared was not matter but behavior. And that void, though invisible, weighed on all who had observed it. As observatories worldwide processed data accumulated during perihelion and subsequent weeks, a clearer, though no less enigmatic, picture began to emerge. The numbers did not lie. The 3I Atlas had crossed the closest point to the Sun with thermal and structural stability that defied the most conservative expectations. None of the typical signs associated with an active comet appeared in the records. Space telescopes, from the James Webb to the Solar and Heliospheric Observatory, agreed on an undeniable conclusion. There was no significant sublimation, no dust release, no visible fragmentation. It was a body that in physical terms behaved more like a rock than an icy conglomerate. The James Webb team was the first to publish a detailed report. High-resolution infrared spectra showed a surface coated with silicate compounds and carbon residues. Signatures of water ice, ammonia or carbon dioxide were practically non-existent. Instead, traces of heat-resistant minerals appeared, such as olivine, pyroxene and feldspar. Materials typical of rocky bodies that have undergone prolonged heating and cooling processes. That composition suggested the 3I Atlas was not a classic comet, but a hybrid object formed in a region of space where volatile elements had already been lost millions of years ago. Probably, temperature measurements taken during perihelion surprised even more. Thermal models indicated the 3I Atlas surface should have reached temperatures near 600 degrees Kelvin, enough to vaporize surface ices. However, the thermal emission spectrum remained constant, without peaks or drops. This meant heat distributed uniformly or the surface acted as a thermal shield. That property was extremely unusual. Porous bodies or those covered in fine dust tend to heat unevenly, producing more active regions than others. The 3I Atlas, in contrast, seemed to have high thermal conductivity and very low emissivity, as if its skin were composed of a compact material hardened by centuries of cosmic radiation. In NASA's Astromaterials laboratories, scientists began comparing 3I Atlas data with the oldest meteorites recovered on Earth. Some carbonaceous chondrite fragments showed similar surface properties, outer layers burned by prolonged heat exposure, followed by a less altered porous interior. In samples, those carbonized layers acted as thermal barriers preventing internal material sublimation. The 3I Atlas behavior could be explained similarly, a hardened crust protecting a more fragile interior. However, the question remained how that layer could form outside a solar system in the extreme cold of interstellar space. The ALMA observatory also provided key information. Its antennas detected subtle variations in the object's reflectivity at millimeter frequencies, allowing inference of surface roughness. The 3I Atlas was not completely smooth but irregular, with microstructures that scattered light unevenly. Those irregularities, though small, were consistent with a surface coated in melted minerals that had solidified slowly. According to calculations by the Chilean team analyzing the data, the object must have had an outer layer at least 10 centimeters thick formed by melted or vitrified material, reinforcing the idea of a thermal self-protection process. Information about its rotation also proved revealing. Before perihelion, photometric observations indicated irregular rotation, with slight period variations. After perihelion, the spin became more stable. This change was not random, it meant the object had reached a new dynamic equilibrium. Normally, comets undergo chaotic rotation changes due to uneven gas expulsion. But in this case, with activity ceasing completely, the 3I Atlas stabilized its axis. Its now constant rotation was indirect proof of its total inactivity. Computational models developed by the European Space Agency simulated thousands of possible scenarios to replicate observed data. In all cases where the object maintained integrity without activity, results required an average density higher than 2 grams per cubic centimeter, much higher than known comets, which are usually spongy bodies with densities near 0.5. This implied the 3I Atlas had a solid structure, not a mix of ice and dust, but a compact nucleus similar to metallic or rocky asteroids. If confirmed, it would be the first directly observed interstellar object of that type. The Hubble telescope, with its optical vision, added another important piece to the puzzle. Images taken on the 12th and 13th of November showed a body with defined contours without any visible halo. Scientists used image stacking techniques to detect possible dust traces, but found nothing. The conclusion was clear. If the 3I Atlas had released any material, it was so scarce that its surface density must be less than 16 grams per square centimeter, a practically undetectable figure. It was as if all its activity had ceased abruptly in a matter of hours. Reflectivity analyses confirmed a very low albedo, close to 0.04, meaning it reflected only 4% of incoming sunlight. This value placed it among the darkest bodies ever observed, even darker than many outer belt asteroids. Such a dark surface absorbed much radiation but dissipated it uniformly. That combination reinforced the carbonized shield theory. Organic compounds degraded by extreme radiation can become black, dense, and thermally stable, something observed in laboratory experiments but never in a real interstellar object. Polarimetric spectrum measurements from the Keck telescope revealed an unexpected detail. Light reflected by the 3I Atlas showed very low linear polarization. This type of signature is typical of smooth surfaces or those composed of extremely small grains. In the 3I Atlas case, it suggested a compact surface without loose dust, possibly vitrified. It was a phenomenon consistent with the idea that the object had undergone partial surface melting during perihelion, hardening its outer layer. From combining all that data, astronomers began building a detailed physical model of the object. According to simulations, the 3I Atlas could have a diameter estimated between 90 and 150 meters and an elongated shape with an axis ratio close to 3.1. Its average density and mineral composition made it an intermediate body between comet and asteroid, something like a fossil nucleus that had lost its active properties long ago. The absence of volatiles, thermal uniformity, and rotational stability formed a set of evidence difficult to refute. In official communications, scientists began using a new phrase, non-active interstellar object. With it they tried to describe a phenomenon that did not fully fit any existing category. It was not a comet because it showed no sublimation, nor a common asteroid, because its trajectory was hyperbolic and its composition did not match solar system bodies. It was literally a petrified interstellar traveler. The data also revealed a detail that initially went almost unnoticed. Before perihelion, the 3I Atlas presented slight color variability with greenish tones that disappeared after its sun passage. That chromatic change confirmed by spectral analyses implied the surface had undergone a real chemical alteration. Molecules producing the green color, mainly cyanogen and diatomic carbon, were completely destroyed, leaving a more neutral surface. This seemingly minor fact was actually direct evidence that the object had experienced an irreversible transformation. Over time, scientists understood that what the 3I Atlas revealed was not an anomaly, but a lesson. It showed that interstellar objects could evolve in ways very different from local comets. Some, hardened by eras of cosmic vacuum exposure, arrived in our solar system turned into immortal relics. Others, like Borisov, disintegrated rapidly upon feeling solar heat. The 3I Atlas belonged to the first group, those that survived but at the cost of losing all activity. In graphs, numbers, images, astronomers saw more than data. They saw evidence of a natural process taken to the extreme, a body that had crossed the sun's fire and emerged intact, but transformed. What the data revealed was not just a resistant object, it was a silent testimony of cosmic time, a traveler from another star that upon passing hours left a message engraved on its dark skin. The universe can forge matter so resistant that not even the sun can break it. The 3I Atlas passage through perihelion not only marked a historic moment for observational astronomy, it also triggered a quiet revolution in how scientists understood interstellar matter. Until then, models about comets and asteroids from other systems were based mainly on what was known from the solar system. Astronomers assumed physical and chemical processes were universal, that ice behaved the same everywhere, and that solar radiation always had the same effects. But the 3I Atlas changed those rules. Its anomalous behavior, resistance, and absence of activity after perihelion forced researchers to reconsider the very foundations of astrochemistry and planetary formation. In the weeks following its sun passage, universities and observatories worldwide began organizing emergency conferences. The data were too consistent to be dismissed as error, but too strange to be explained with current theories. At the Paris Observatory, a group of researchers proposed a bold hypothesis. The 3I Atlas might have formed in a space region where planetary accretion processes occurred at much higher temperatures than known. That would mean its composition was based on materials that melted and solidified again, generating an extremely resistant internal structure. If this theory were true, the object would not be a frozen comet, but a hardened mineral fragment, a kind of rocky fossil ejected from its original system during a collision or gravitational perturbation. NASA, for its part, formed a special committee with experts in small body dynamics, astrochemistry, and thermal physics. Its goal was to analyze all possible variables. Preliminary reports indicated the 3I Atlas behavior could not be attributed solely to its composition. There was something in its structure that allowed it to dissipate heat unusually. Calculations showed that despite receiving enough solar radiation to sublimate ice in minutes, the object maintained nearly uniform surface temperatures, without reaching expected critical levels. This characteristic could be due to a combination of high thermal conductivity and low internal absorption, turning the 3I Atlas into an excellent energy dissipator. In Europe, the European Space Agency also published its conclusions. The report described the 3I Atlas as a body representing a new type of interstellar matter, more resistant than any material observed in solar system comets or asteroids. According to European Space Agency models, prolonged cosmic radiation can induce structural changes in dust grains and organic compounds, making them denser and more stable. This process, called interstellar metamorphism, could explain why the 3I Atlas survived perihelion without damage. In essence, its surface would have undergone millions of years of energetic bombardment, transforming it into a natural armor. The scientific community realized the phenomenon had much broader implications. If bodies like the 3I Atlas traveled between stars, then planetary formation models had to expand to include processes generating ultra-resistant materials. This in turn changed perception about protoplanetary disk composition. Scientists began talking about a new body category: hardened interstellar nuclei, fragments of ancient planets or planetoids ejected from their origin systems that travel for millions of years until encountering other stars. In laboratories, material specialists began replicating interstellar space conditions using vacuum chambers and extreme ultraviolet radiation sources, trying to recreate time effects on organic compound and mineral surfaces. Results were surprising. In a matter of weeks, materials subjected to constant radiation developed dark, compact, and surprisingly hard layers. Measuring their thermal conductivity, researchers discovered those layers acted as nearly perfect insulators. It was the same principle that seemed to protect the 3I Atlas from sun heat. These tests supported the theory that the object was not an anomaly, but a sample of a universal physical process that had gone unnoticed until then. The news also impacted astrobiology. If interstellar objects could travel for millions of years without disintegrating, that meant they could transport complex organic compounds between stellar systems without destruction. Though the 3I Atlas showed no signs of containing active biological molecules, its mere existence demonstrated organic material could survive extreme conditions. In an article published by the University of Cambridge, astrobiologist Andrea Murillo summarized it forcefully. These objects are time capsules. They carry with them the primordial chemical building blocks of other systems and preserve them intact for entire eras. The 3I Atlas reminds us that life could have a much broader reach than we imagine. In academia, the 3I Atlas case prompted a profound review of cometary evolution models. Until then, astronomers classified comets by activity level: active, intermediate, or extinct. But the 3I Atlas fit none. It was not active but neither extinct, it showed no erosion or wear signs, and its structure remained intact. Therefore, the International Astronomical Union discussed creating a new category: passive interstellar objects, bodies that were once active but have permanently lost their volatile sublimation capacity. That definition was provisionally adopted at a 2026 Congress, making the 3I Atlas the first official member of this new cosmic class. Meanwhile, public interest grew. Images captured by the James Webb spread worldwide, showing the 3I Atlas as a dark point defying sunlight. Though not spectacular to the human eye, its scientific importance was monumental. Documentaries and popular articles explained this object was proof interstellar matter could be far more complex and resistant than thought. Space agencies seized the attention to promote new missions dedicated to studying this body type. One of the most ambitious proposals emerged from a NASA and European Space Agency consortium: send an interceptor probe capable of studying an interstellar object in real time. The mission, called Stellar Passage, would be designed for launch in the 2030 decade and use advanced electric propulsion to reach speeds allowing interception of a body similar to the 3I Atlas. The idea was to capture dust or gas samples, if any, and analyze them directly. Though the mission is still conceptual, its development was directly inspired by what the 3i Atlas taught, that every interstellar visitor is an unrepeatable opportunity to understand the universe's material history. In theory, astrophysicists began integrating the phenomenon into galactic evolution models. If millions of fragments like the 3i Atlas travel between stars, they could act as natural messengers, transporting heavy elements and organic compounds from one system to another. This means matter making up our planet could include residues from distant worlds ejected from other systems billions of years ago. In a way, the 3i Atlas reminded scientists the boundary between ours and alien in the cosmos is much blurrier than believed. But the deepest impact was philosophical. The fact that an object could defy solar destruction logic and survive intact led astronomers to reflect on cosmic permanence. Everything known tends to change, disintegrate, transform. However, the 3i Atlas seemed to resist even the most universal principle, that of entropy. Its interstellar journey became a scientific metaphor for cosmic time, proof that structures exist that can endure entire eras without fading. Ultimately, the 3i Atlas left a mark transcending observation limits. It was not just an object that defied science, it was a mirror showing our knowledge limitations. Every datum it revealed expanded the boundary of possible. Reminding scientists the universe still holds secrets beyond any prediction, and though its brightness has faded, its legacy will remain as one of the most valuable lessons the cosmos has offered. The certainty that even the impossible under the sun's gaze can turn out real. After perihelion and initial awe, the 3i Atlas continued its silent trajectory moving away from the sun, while its speed decreased slightly ascending the hyperbolic ellipse. Telescopes worldwide redirected attention to it, determined not to miss any detail of its post-solar behavior. Scientists knew every day counted. The farther it moved, the harder detection would be, and the faint light reflected by its dark surface would soon be lost among background star glow. Still, space agencies and private observatories coordinated to maintain prolonged vigilance, a kind of second global observation campaign to record the object's thermal and spectral evolution. The James Webb was again key in this stage. Its high-sensitivity infrared instruments captured signals confirming the 3i Atlas surface temperature decreased uniformly, without abrupt alterations. This indicated the object preserved structural integrity. If any detachment had occurred, heat would have distributed irregularly. But there were no changes. The surface cooled slowly, almost mathematically, demonstrating notable homogeneity. Data also showed albedo remained extremely low, confirming its carbonized layer stayed intact. Meanwhile, the Hubble telescope began recording almost imperceptible minor brightness variations. Astronomers interpreted this as reflection of its stable rotation remaining around 8 hours per turn. Rotation showed no acceleration or deceleration signs, behavior reinforcing the idea the 3i Atlas was not releasing material or suffering mass loss. Everything indicated that after its sun encounter, the object had entered a prolonged stability phase, a kind of cosmic quietness accompanying it during solar system exit. Ground-based observations, though more limited by distance and decreasing brightness, provided complementary information. In Chile, the Very Large Telescope detected a small light intensity deviation at certain wavelengths, a phenomenon experts attributed to microsurface fractures caused by thermal expansion. These cracks, though minuscule, could explain some reflectivity fluctuations. However, they posed no threat to overall object integrity. The 3i Atlas continued behaving like a solid, resistant body, surprisingly coherent with prior data. Scientific interest was not limited to understanding its current state, it also focused on projecting its future. Revised orbital calculations showed the 3i Atlas would move away from the solar system through the Auriga constellation region, exiting the ecliptic plane at a speed over 42 kilometers per second. In a few decades it would again be in interstellar space, far from sun gravitational influence. Some astronomers reflected on the possibility that in millions of years it could cross another stellar system and repeat the same story. A brief visit, a fleeting observation, and a new mystery. The scientific community understood time was limited. Every observation had to be maximized before the 3i Atlas disappeared from human view forever. Therefore, joint observation programs were organized between NASA, the European Space Agency, the Japanese Subaru Observatory, and the Gemini Telescope Network. The goal was to measure final changes in its brightness, polarization, and thermal emission. Combined data would build a detailed three-dimensional model of its structure, a final portrait of one of modern astronomy's most enigmatic visitors. Scientists also began analyzing its trajectory with greater precision to determine its origin point. Using data collected by the Hubble and the Webb, astronomers at Mount Palomar Observatory traced its orbit backward in time and concluded the 3I Atlas probably came from a region in the Hercules constellation direction. There, millions of years ago, it might have been ejected from its natal system by gravitational interaction with a giant planet. Dynamic models showed a small perturbation could suffice to launch it into a hyperbolic orbit, turning it into an interstellar traveler. That reconstruction, though still theoretical, helped put its long journey in perspective, a crossing that might have lasted tens or even hundreds of millions of years before reaching the Sun's environment. As researchers refined simulations, new projects emerged driven by the interest the 3I Atlas had sparked. One, proposed by the University of Arizona, involved using the ALMA radio telescope network and the Future Square Kilometer Array to track possible background emissions associated with the object's passage through solar wind. Though no artificial radiation was expected, the study would allow understanding how interstellar bodies interact with interplanetary plasma, crucial information for future human interstellar missions. The Vera Rubin Observatory, soon entering full operation, also prepared to search for new objects of the same type. Success in detecting the 3I Atlas had shown interstellar visitors were more common than thought. Before Oumuamua, no one had seen one. After Borisov, some doubted their rarity, but with the 3I Atlas, the third visitor in less than a decade, it became clear our solar system is regularly crossed by fragments from other worlds. With the new telescope, dozens of these travelers are expected to be detected each year, opening the door to a new era in interstellar astronomy. Post-perihelion follow-up results also began integrating into educational programs and scientific simulators. At various universities, space physics students could recreate 3I Atlas surface conditions, testing different conductivity and composition models. Some experiments showed a mix of metallic minerals and amorphous carbon could reproduce observed thermal response almost exactly. Those findings strengthened the idea the object had a rocky origin, perhaps a planetary nucleus fragment ejected after a collision in its original system. Future missions inspired by this event also began taking shape. The American-European Stellar Passage project already understudy plans to develop a spacecraft with ionic engines capable of reaching speeds of tens of kilometers per second to intercept the next discovered interstellar visitor. Learning from 3I Atlas allowed defining necessary instruments, high-resolution spectrometers, precision thermal cameras, and sampling systems designed to capture particles without altering composition. The goal would be to obtain the first direct sample of an interstellar body and analyze its structure at the atomic level. Meanwhile, the public remained fascinated by the story. The images, though modest in appearance, represented something deeper, the tangible presence of another stellar system crossing ours. Every new observation was shared with excitement by observatories and science communicators. For many, the 3I Atlas had become a symbol of connection between worlds, proof that matter travels freely between stars, carrying fragments of unknown cosmic stories. In science, lessons were clear. The 3I Atlas study demonstrated interstellar matter diversity is much greater than thought. It also taught astronomers classic categorization between comets and asteroids is no longer sufficient. New definitions, new scales, new models are required. And most importantly, it showed every object crossing our solar system can completely change understanding of how matter forms and evolves in the universe. Over time, the 3I Atlas brightness continued decreasing until beyond most optical telescopes' reach. Only the most sensitive instruments like the Webb, the ALMA, and the Rubin could follow it. But though its light faded slowly in the distance, its scientific legacy continued growing. Data collected during its sun passage would continue being analyzed for years, perhaps decades, feeding new theories and comparisons with future visitors. Every number, every image, every measurement formed part of a larger mosaic, the constructing portrait of matter traveling between stars. When it finally disappeared completely from our detectors, the 3I Atlas would continue existing, wandering in darkness, unaltered, carrying its origin secrets. Astronomers knew they would probably never see it again, but also understood it had left a permanent mark. Its brief passage had expanded human science's horizon. In silence, the object moved away. But its echo would continue resonating in laboratories, scientific articles, and the imagination of all who had followed its journey. The 3I Atlas became, unintentionally, one of modern astronomy's greatest silent teachers. Its solar system passage not only brought data, it brought an intellectual and philosophical challenge to an entire generation of scientists. From its 2024 discovery, it was followed with expectation, studied with precision, and debated with passion. Every observatory, from the Hubble to the James Webb, pointed instruments at it hoping to witness a spectacle of gases, dust, and light. Instead, the cosmos showed them something else. The value of silence, the teaching of resistance, and the presence of the inexplicable within the possible. What seemed an opportunity to observe interstellar body destruction transformed into the lesson of how something can survive the sun's fire without changing. That paradox became the starting point for a new understanding of cosmic matter. Researchers learned the 3I atlas was not a statistical error, but a window into a body class defying traditional comet and asteroid notions. Its resistance was not an exception, but evidence of processes occurring beyond solar system limits. In regions where cosmic radiation, vacuum, and time shape materials until turning them into nearly indestructible structures. The 3I atlas taught that interstellar space is not an inert abyss, but a natural laboratory transforming matter. Cosmic rays, high-energy particles, and temperatures near absolute zero are invisible sculptors slowly modifying bodies traveling between stars. What arrived in our system was perhaps the result of millions of years of exposure to that extreme environment. Once formed, its nucleus was enveloped in a hardened layer acting as a thermal shield, preserving it even against direct solar radiation. In other words, the 3I atlas did not defy physics laws, it confirmed them in their purest form, reminding that nature always finds equilibrium forms beyond our immediate comprehension. In months following its departure, scientists continued discussing its behavior implications. Some theorists argued these objects might be more common than believed and that active comets are actually a minority in the universe. If true, that would mean most interstellar bodies travel space without visible signs invisible to our telescopes until luck brings them close enough for detection. The 3I atlas would then be one of the few visible examples of an immense silent population of cosmic travelers crossing stars without leaving a trace. Its observation also changed how humanity perceives the concept of origin. On Earth we usually speak of the sky as something distant, alien, far. But every interstellar dust fragment, every rock like the 3I atlas reminds us everything composing planets, including ours, was born from the same universal processes. There are no true boundaries between stellar systems, only paths connecting them. Carbon atoms today part of our atmosphere might have been part of an object like the 3I atlas billions of years ago, in a time before even the sun. Thus this interstellar visitor became a mirror of cosmic past and at the same time a clue about our own origin. The fact that the 3I atlas survived perihelion without destruction signs demonstrated the universe is more varied than human models had imagined. Comets are not simply dirty snowballs, nor asteroids simple rock blocks. Intermediate forms exist, hybrids, hardened relics telling different stories. This discovery broadened the possibility spectrum in small body classification, opening new research paths. Now, when astronomers analyze new objects, they do so with a different perspective. They no longer seek only activity signs, but also evidence of anomalous stability, vitrified surfaces, and resistant compositions that may indicate interstellar origin. In laboratories, simulations inspired by the 3I atlas continue revealing valuable information. Materials that might behave similarly are studied, trying to understand the internal structure allowing survival. It has even been suggested that analyzing its properties could teach new thermal protection techniques for future space probes. Applied science also found utility in a phenomenon that at first glance seemed purely theoretical. The 3I atlas behavior against extreme heat could become a model for designing advanced materials capable of withstanding solar radiation in sun-closed missions or even to other stars. But beyond science, there was something almost poetic in all this. The 3I atlas traveled for millions of years, crossed empty regions, passed through absolute darkness, and when it finally approached our sun, it did not explode or fragment. It remained silent, whole, indifferent. It was a demonstration of human humility before the cosmos. For centuries, humanity looked to the sky seeking great spectacles, explosions, lights, but sometimes the deepest teaching is found in what does not happen, in quietness, in the object that does not change, but precisely because of that transforms everything we thought we knew. When the object began fading from optical instruments, many astronomers felt a kind of melancholy. They knew it was the last time they would see it. On screens, the 3I atlas reduced to a weak light point slowly moving away into darkness until disappearing. However, its departure was not an end. Every bit of information collected during its solar system passage remained recorded, analyzed, and archived for future generations. In that sense, the 3I atlas never left. Its story was written in data, scientific articles, in researchers' minds who learned from it. Cosmos poets, as some call popularizers, said the three-eye atlas had passed before the sun to teach us what light cannot show. And they were right. This visitor brought a silent lesson, that of cosmic time, persistence, and human knowledge limits. In its apparent immobility, it showed the universe does not always reveal secrets with noise and movement, but with equilibrium and permanence. When its final coordinates were projected, the three-eye atlas was already traveling toward the Auriga constellation, moving away at more than 40 kilometers per second. In a few decades, its weak reflection would be lost among stars, but in humanity's memory its passage will remain recorded as one of modern astronomy's most fascinating moments. It was the visitor that left no visible traces, but an indelible mark on the minds of those who observed it. The mystery of what was missing in the three-eye atlas will remain open. Perhaps we will never know exactly what changed during its sun encounter or what internal processes caused its sudden silence. But that in the end is what keeps science alive, recognition that questions still lack answers. And while the three-eye atlas continues its path to infinity, humanity will keep looking at the sky, waiting for the next traveler, the next fragment from another star to remind us once more that everything is connected, because the universe ultimately does not speak to us with words or explosions, it speaks with presences crossing our sky and leaving, giving us certainty that knowledge is a journey, not a destination. The three-eye atlas was one of those messages, a silent visitor that taught us that even the impossible under the sun's light can be real,